All right, properties and limits. Don't write everything word for word, please. All right, it'll take forever. And in that last section, you learned that as f of x approaches x, c does not depend really on the value of x for that function. However, for some of them, that the limit is exactly precisely f of c. That means the actual height is the intended height. So yesterday we talked about a lot of these functions, you can just use direct substitution. Okay, so the big idea here, direct substitution, is just evaluating that function at that c value. Okay, so this would be the big idea. Direct substitution means this. We just directly substitute x, that value of x, into the function. So the limit as x approaches c of f of x is just f of c. So here you go, properties and limits. It's a lot of notation right now, a lot of notation. Some basic limits. If b and c are real numbers and n is a positive integer, has to be a positive integer, or it creates the reciprocal for those exponents. Limit as x approaches c, and remember c is just some value on the x-axis. Okay, the limit as x approaches c of a function b, that means a number function. Okay, that means a constant function, is just b. Okay, how would that look? Not like that. How would that look? Say we have coordinate plane, we have a function that is the height of b. So that'd be a constant function, right? This would be f of x equals b, some height. Okay, if we have some x value c, what's the limit as x approaches c of this function b? Well, it's the actual height of the function, which is every height of the function. And it's just a constant function. Okay, people get confused because they see just a number out here, they don't know what to do. Guys, that's just a constant function. All right, number 2. The limit as x approaches c of x. X itself is just a linear function. Just plug in c and you get c. This would be the linear function, direct variation. If we're over here at c, the height itself would be c also. Right? If your function is f of x equals x, plug in 1, what do you get? 1. Plug in 2, what do you get? 2. And then this one, this right here is a polynomial one. This would be our polynomial function. N is a positive integer, so x squared, x cubed, x to the fourth, x whatever. Polynomials are friendly functions, they're continuous everywhere. All you do is directly substitute c. The limit as x approaches 2 of the function 3. Is it 2? Is it 3? I don't know what the answer is. Well guys, this is a constant function. Constant function has a constant height. The height is always 3, no matter what the x value is, right? So what's the answer here? 3. How do I know that also? Do you guys see a place to substitute x anywhere? I don't see one. So it doesn't matter what x is. The height's always 3. The function's always 3. Okay, and then for part B, linear function, continuous everywhere, direct substitution, you get 4. See if I got another one. Ooh, x squared. This seems light work compared to yesterday, right? Okay, and what do we get for this one? Just 4. This would be definitely a direct substitution. We have a polynomial with a positive exponent. Substitute 2 in for x. 2 squared is 4. All right, some more properties. Now we have some qualifiers here. We got b and c being real numbers. N is a positive integer again. F and g are real functions, or I should say they are functions, with the following limits. Okay. If we approach c for f of x, the limit is L, and L is just some number, okay? If we have the limit as x approaches c for the function g, that is k. K is just some real number. What they're saying here is f and g have limits as x approaches c, and these are the two heights. For f of x, it's L. For g of x, it's k. Number one, scalar multiplier. That's just a scalar multiplier. If we have some limit as x approaches c of some scalar multiplier b, which just means a number times something, times f of x, that equals b times L. Now I don't like the way the book writes this, so we're going to add a step. Okay, I'm just going to cross this out right here. I'm going to say, well, if we have a scalar multiplier on our function, we can actually take that scalar multiplier and put it in front of the limit, actually. Okay, so if we have a scalar multiplier, we just put it in front. The limit as x goes to c of f of x, well, that's L, so now we just have b times L. Remember, c is a real number, b is a real number, f of x is just a function. Sum or difference property, again, I'm going to have a middle step. If we have the limit of a sum or difference, that means two different functions, maybe what can we do? We can actually break them apart into individual limits. We can say this is the limit as x approaches c of f of x, plus or minus the limit as x goes to c of g of x. And the limit as x approaches c of f of x is L. The limit as x approaches c of g of x is k. And so now we just have L plus or minus k. I think this middle step is extremely important. You'll see that as answer choices every once in a while on the AP test. Multiple choices. Okay, what if we have a product? If we're trying to evaluate a limit and there's a product, maybe one of these two functions is confusing, you can actually break this up. The limit of a product is the product of the limits. Limit as x goes to c of f of x times the limit as x goes to c of g of x, and that equals L times k. So basically what you're seeing here is you can break these limits up. Does it work for quotients? Yes, except for the limit as x approaches c of the bottom function g of x cannot be 0, or that fraction is undefined, obviously, right? So again, we'll have that middle step. I'll skip this. I'll go way over here. Go limit x goes to c of f of x over limit x goes to c of g of x. Top limit is L, bottom limit is k. And we did this yesterday, those rational functions. That numerator was its own function, actually. The bottom, the denominator, was its own function. We just looked at the limit of the top, limit of the bottom, or we direct substitute in the top, directly substitute in the bottom, and evaluated. And we always made sure that bottom limit was not 0. And then the power property. Some people might not like the way I'm going to write this, but that's okay. And by some people, I mean some mathematicians. They'll get over it though. So that's basically what's happening, guys. If you have a power inside, you just take that function, find that limit and raise that limit to the power. So it'll be L to the N. How would that one look? How would that be different than, say, like a polynomial function? Maybe we have like x squared plus 3x plus 4 raised to the 5th power, and we want to find the limit as x goes to 1. Well, figure out what the limit is on the inside and raise that power to the 5th power, or that number to the 5th power. And that's how direct substitution would work anyways, right? So they're basic, they're, I don't know, intuitive, pretty easy. The notation is just a train wreck sometimes. I think sometimes at the beginning of calculus, that's what we have trouble with. Hence delta x. All right, now we did this yesterday. You can see right away, ooh, that's a nice polynomial. We can find the limit, but it's directly substituting. We can plug in 2, boom, we're done, and we like that because it's kind of like, I don't know, our thing. We like to do algebra. We like to do algebra, okay? But check this out. Let's overcomplicate this. All right, we have a sum or difference, right? We could break this up using the sum or difference, right? Let's do it. Limit. Using our properties, we could rewrite this sum. Okay? Yeah? Oh, in this one we have a product. We could bring that 4 out in front. We have a scalar multiplier. Is there anything else we could do? We do have this power here. We could go do that, I think. And using properties explains why just direct substitution works also. Helps explain it, or is another way to explain it. This answer is just 3, this is 2 squared, which is 4, 4 times 4 is 16, right? Okay, so if they ask you to expand the limit using the properties, this is what we're talking about. Kind of similar to logs a little bit, remember that? Using the properties of logs to expand or condense things, kind of similar. All right, next property. Now, I don't know if I really write much of this down. We've already done this. We have a polynomial function. We already did this at the beginning, right? Basically. If we have a polynomial function, they use p of x for polynomials a lot of times. If we have a polynomial function, we just directly substitute. Okay, that's common knowledge. I don't know if we really need to write all this down. Okay, we have a rational function. A lot of times use r of x for rational functions, obvious reasons. Okay, p's over q's. Okay, if we have a top function p of x, bottom function q of x, before we directly substitute, we just got to make sure that when we substitute c into the denominator, the answer is not 0. We did that yesterday. I don't know if we really need to write much of that down. Okay, and they're just saying for rational functions directly substitute, just make sure the 0 is not in the denominator. Okay, this is an over mathy way of saying that. So this one's not too crazy. We've done it. We've looked at it before already. Limit a rational function. Before we even attempt this problem, what's the first thing that goes to your mind?
Direct substitution.
Where?
Like the 1 for the x.
Where?
Everywhere that there's an x.
And
Well,
then
I
what?
guess in the bottom to make sure it's not a 0. first.
Yes, I always just substitute in the denominator and be like, okay, is that 0? Because I'm not going to write it all out with 1s everywhere. I'm just going to mentally check in the denominator. If I substitute a 1, is the denominator 0? If it is, that means more work. Okay, then I back up, I look at it a little bit different. Do I need to factor and cancel? Do I need to do all those things? Okay, now let's see if we can be extremely extra and rewrite this, expand this whole thing using limits in one step. I don't want to write 5 steps out. Okay? So we know the limit of a rational function is the limit of the top and the limit of the bottom, right? And then I know if we have a sum or difference, it's the same thing as the limit of everything added together. And then we have this polynomial or this exponent that can go on the outside. Let's see if we can expand this in one step. Okay, let's put the limit up on top. Limit x goes to 1 of x, and then we can square that limit, right? Plus limit as x goes to 1 of x, plus limit as x goes to 1 of 2, all over. Now we put the limit in the bottom. There we go. That's as much as we can expand this. And yes, I just want you guys to directly substitute all the time. However, you just have to have this knowledge in the back of your mind that maybe they might have a random expand this using a properties of limits question, and you got to know this could be true. Okay? How high in the priority list is this? Not really. Good? All right, how about a radical? Radicals, do we do much direct substitution with radicals yesterday at all? I don't think so, did we? So we might want to pay attention to this a little bit closer. Let n be a positive integer. Okay, if n is a positive integer, that means we're taking positive roots, correct? So we're not taking negative square roots. We're taking positive, like cubed root, square root, fourth root, fifth root, whatever. The following limit is valid for all c if n is odd, and is valid for c greater than 0 if n is even. What does that mean? That means if n is odd, you're taking a third root. Can you take a third root of a negative number? Yeah, right? But if n is even, the radicand has to be positive. You can't take a even root of a negative number, right? So that's all they're saying, and we have to watch out for that. Bless you. Composite functions are next. We have not worked with that yet. If f and g are functions such that, again, the limit as x goes to c of g of x is L, and then the limit as x goes to L of f of x equals f of L, then, now you guys work with composite functions a little bit, right? Work inside out, correct? Okay, notice what they did here. If you have a limit of a composite function, you find the limit of the inner function, find the limit of the inner function. That's what this means, find the limit of the inner function, and then just evaluate the outer function at the inner function limit. So at the answer to that limit you found, evaluate the outer function. We'll work with this. We'll work with some special limits, some special composites. The AP people, the College Board, they like composite functions lately. Qualifiers. The outside function must be continuous at the limit of the inside function to be able to do this. That means this limit, it must be continuous. If you find the number here, f better be continuous at that number you found in here. If it's not, we got to do something else. It takes more work. Okay, questions? This will be much easier. We'll bring some clarity to this. Don't worry when we do some practice problems. It's going to be confusing at first. The whole year is going to be confusing at first. Then you'll get it. Easy one. Because sine is continuous everywhere, it's a direct substitution. Cosine's continuous everywhere, direct substitution. Tangent is not continuous anywhere, everywhere, but look at that, they said if C is a real number in the domain of the function. So they're already saying, hey, that number C better be in the domain of the function, just direct substitute then. Cotangent, remember, is the reciprocal of tangent. Secant is the reciprocal of cosine, and cosecant is the reciprocal of sine. Two special limits. The limit as x goes to 0 of sine x over x equals 1. We've got to memorize that. The limit as x goes to 0 of 1 minus cosine x over x equals 0. Got to memorize that. All the time people will say the second one does not exist. Why? Because if you directly substitute 0 in for x, you get 0 in the denominator, right? And cosine of 0 is what? 1. You have 1 minus 1 in the numerator. That's 0 over 0. And they'll say, God does not exist. Nope, it actually exists, and the answer is 0. You got to memorize this one. Okay, let's do a practice problem here finally. Let's say we have this function. Limit as x goes to 0 of tangent x over x. Right away you're going to say, well, there's 0 in the denominator, so it does not exist. Nope, 0 in the denominator means more work. Okay? Well, I don't know what to do. It looks like the sine one. It does, doesn't it? However, when you're trying to go about figuring stuff out with tangent, in pre-calc, what'd you guys do? When you're doing all those like properties, or you're doing those trig proofs, you guys remember that? When you don't know what to do, what do? Rewrite in sines and cosines. Okay, so anytime you have tangent, you don't know what to do, I'd rewrite it with sines and cosines. Okay, let's do that. Again, we had this thing going to 0 over 0 because tangent of 0 is 0, right? We have 0 over here. We got 0 in the denominator. Means more work, so let's do it. First thing, rewrite using sines and cosines. So that would be sine of x over cosine x over x. Ooh, we have a complex fraction. Let's fix that. And the limit, x goes to 0, sine of x over cosine x times 1 over x, multiplied by the reciprocal. Now we're multiplying. We have two factors. We don't need parentheses. If you want to put them, you can though. Does anything look familiar that you might need to have memorized? What if I change the order, because in the denominator or the numerator we're multiplying, right? What if I do this? Because we can change the order of multiplication, right? Well, what's the limit as x goes to 0 of sine of x over x?
1.
That's 1. And using the properties and limits, if we have a property or the limit of a product, it's just a product of the individual limits, right? Let's take the limit of this guy. We got 1. What's the limit of 1 over cosine x as x goes to 0? 1. So cosine 0 is 1. We have 1 over 1, which is just 1. 1 times 1 is 1. So at first, we thought this was going to be does not exist or undefined. But again, if you have 0 in the denominator, it means more work. Do some algebraic manipulation. If you have tangent, the key is right sine and cosine and move things around a little bit. Okay, so this limit would be 1. Okay, and then this one's a pretty popular one, very similar to ones that are always on the AP test. This looks really similar to one of those trig limits we have to have memorized, but we have a problem. There's a 4 inside of sine, right? And heaven forbid, if you try and factor out a 4 out of the argument of sine, seriously, I hope the math gods strike you down or something. Like, you can't take that stuff out of there. Okay, it has to stay in there, right? Okay, 4 needs to stay in there. You can't factor it out. However, it'd really be nice if we had a 4 down here, right? We have sine of 4x over 4x. It'd be the same argument over the denominator. That would be 1. Or was that 0? Which one is it? What's sine of x over x? The limit is x goes 0. 1? Okay, 1. So that would be 1. How can we get a 4 down here? Well, multiply by 4 over 4. That's 1, right? Doesn't change the value of anything. We can bring this inside. I'm going to go 4 times sine 4x. And because we're bringing the 4 over 4 in, we're multiplying across the bottom, I can move that over here. The limit as x goes to 0 of 4 is 4. It's a constant function, doesn't matter what the x is. What's the limit as x goes to 0? Sine 4x over 4x. 1. As long as the argument of the trig function and the denominator are the same, that limit will be 1.